Welcome to qnawire.
Okay, we've got a couple sets of vectors here. One set is the set of vectors -3, 1, 2, 2, 4, 1, and 1, -1, 2. And we need to find out, are these orthogonal with respect to the Euclidean inner product on R? Well, what does that mean? Well, what is the inner product on R? That's what we know as the dot product. So if we wanted to take the dot product of the first and second vectors, that'd be -3 times 2 plus 1 times 4 plus 2 times 1. That's our familiar dot product. That's the inner product on R3 of these two vectors. And the answer, in fact, is 0. And if two vectors are orthogonal to each other, the dot product will be 0. So we can already say that those two vectors are orthogonal with respect to the inner product on R3. So all that remains is for us to check this for the remaining vectors, or the remaining possible combinations of these vectors, so the first and the last. Now let's do that. -3 times 1 plus 1 times -1 plus 2 times 2 minus 4, or -3 minus 1 plus 4, once again 0. And finally, we can check this final combination, and we get 2 times 1 minus 1 times 4 plus 2 times 1. Once again, we get 0. So we can confidently say that this set S is a set of our orthogonal vectors uh, in with respect to the Euclidean inner product on R3. Now, what about this final set? We've got 1/3, 2/3, 2/3, 2 over root 5, -1 over root 5, 0. That's good. And 2 over 3 root 5, and 4 over 3 root 5, and -5 over 3 root 5. Okay, well, definitionally, what does it mean to be orthonormal? To be orthonormal means that all the vectors are orthogonal, just as they were in our initial case, but also that they've all got magnitude 1. So that means if I take a given vector and take its magnitude, that's going to be equal to 1. That's what it means to be normalized. So if they're orthonormal, that means if I take their dot products, they'll be 0. And if I take any individual vector and calculate its magnitude, that should be 1. Well, how do we determine the magnitude of a vector? We simply take the dot product of it with itself. And that dot product, that inner product of the vector with itself should give us uh, the magnitude, and that will tell us whether it's normal or not, normalized or not. So let's start with the first one. Let's just check if they're all normalized, and then we'll start checking if they're orthogonal. So we get 1/3 times 1/3, right? Dot product with itself, plus 2/3 times 2/3 plus 2/3 times 2/3. Okay, what do we get? We get something over 9, and it's going to be 1 plus 4 plus 4 equals 9 over 9. That looks like a 1 to me. So that first vector is indeed normalized. It has magnitude 1. Let's check the second one. We've got 2 over root 5 times 2 over root 5 minus, or let's do plus 1 over root 5 plus 0. Sorry, this should be squared. Everything needs to be, yeah. So you can just square it, or, I'll follow the convention I've been using up until now, which is that I was just multiplying it by itself. Either is fine. Plus 0 times 0. Okay, great. If we add this up, we know we're going to get 5 in the bottom, and we're going to get 2 times 2 plus 1 plus 1. That looks like 5 over 5, or 1. That looks normalized to me. Okay, now the final vector is 2 over 3 root 5. This is the other way we can do this. We can just square this. Plus 4 over 3 root 5 squared plus negative 5 over 3 root 5 squared. And we're going to have to do equals on the next line. So we ran out of space. Okay, so what's the denominator going to be? It's going to be 3 root 5 squared. That looks like 9 times 5 to me, or 45. And up top, we're going to get 4 plus 16 plus 25, or that looks like 45. Hey, the bottom also looks like 45, and that's a 1. So great. Everything is normalized. Now we just need to compute the dot product of each of the vectors with each other and determine if they are indeed orthogonal. Okay, so let's let me move this down so we have some fresh space to work with. Bear with me. Great. Let's clean up a little bit and go back to drawing. Okay, great. So 1 over 3 times 2 over root 5 plus 2 over 3 times negative 1 over root 5 plus, well, this is easy. It's just going to be 0. Great. I can tell already that this is going to be 0 because we've got 1 times 2 plus 2 times negative 1. The denominators are the same. Doesn't matter. Plus 0 equals 0. So 0 plus 0 equals 0. That looks good. Let's check the first vector and the third vector. 1 over 3 times 2 over 3 times root 5 plus 2 over 3 times 4 over 3 root 5 plus 2 over 3 times negative 5 over 3 root 5. Let's check it out. The bottom we know is going to be 9 root 5. Okay, we really don't need the bottom because it's either going to be 0 or it's not going to be 0, but I see 2 plus, should be a minus, okay, plus 8 minus 10. That's 0. We're good. And the last two to check is the second vector and the third vector. And I didn't leave myself a lot of room, but that's fine. Let's say 2 over root 5 times 2 over 3 root 5 plus negative 1 over root 5 times 4 over 3 root 5. And the last element is going to be multiplied by 0 again, so that's not too important. And I see in the numerator, knowing that the denominators are going to be equal, I see that the numerator is 2 times 2 minus 4. That looks like a 0 as well. So that second set are both each individually normalized, and then together they are orthogonal. So therefore, the entire set is orthonormal.